I'd like to acknowledge a few of our industry partners on this project. So we have the Wellington Electric Boat Building Company. They're the company that was set up specifically to build this vessel. Designers and integrators of the electrical system. And then we have SSC Marine, who are doing the naval architecture. And I work for a company called Gurit. We're a Swiss-owned company, but we've actually been based here in New Zealand for over 40 years. And we're a composite technology company that operates mostly in the wind turbine industry, but also in the lightweight industry. And we're a company with a strong passion for environment sustainability. And in fact, we took steps last year as a company to become climate CO2 neutral. For the things we couldn't inset, we offset with a wind turbine facility in India producing renewable energy. And so as a company, what we do is we supply composite materials across these two industries. And within the lightweight, so we have the wind energy and lightweighting. Within lightweighting, we do structural engineering for composite structures. And the structural engineering part of the business is where I sit. So I'm the engineering manager for Gurit Asia Pacific. And the majority of the work in our area sits primarily within the marine sector, but also within the industrial sector, which takes on transport, cars, buses, and also architecture. I can try it a little closer. Okay, we'll try that. But this is the project we're here to talk about today. Right now, this is the newest ferry in the country, and it hit the water for the first time on Friday last week. Now, she's a high-speed commuter ferry, and one of the first vessels in the world to take on the challenge of doing a high-speed vessel and putting it on a regular commuter run. She's not a demonstrator, she's not a technology incubator. This is a fully functional commercial vessel and will be in service later this year. And there's a commercial vessel, there's a customer at the end of this. And fortunately, one that was brave enough to take on such a technically demanding project. East by West Ferries has been the operator of Wellington's cross-harbour service for many years now, and has long been an advocate of efficient marine propulsion or marine vessels. Now, in the year 2000, they traded in a very outdated steel catamaran that they were operating at the time for a fairly modest catamaran down the bottom that was built in 1995, and it revolutionised their business in terms of the fuel consumption and the cost saving that they made in their day-to-day operations. And so 5 years later, they commissioned a brand new boat, one on the left there, slightly larger, along the same lines. Now, both of those were designed actually by Malcolm Tennant and feature high-speed displacement hulls underneath. They're both relatively lightweight built. They're actually foam core timber construction. And the second one was built here in Whangarei. Now, both of those vessels were designed specifically for the Whangarei route, for the Wellington route, sorry. So they're sized in terms of the number of passengers that operate on that route daily. Now, as we fast forward 12 years, and again, they were ready to expand the fleet, and they wanted to continue their tradition of pushing the boundaries with efficient vessel design. And they commissioned a brand new vessel this time. In the intervening years, the level of technology, particularly around electric propulsion, has started to mature. It was still pretty fringe when we first started talking about this project in 2018, and particularly for this size of vessel. But with a customer with a history of wanting to strive for efficiency, it seemed like a good fit and something they were willing to look at. And what's more, they had an ambition to build and design this project in New Zealand. They had gone to market looking for other ones, but key to the customer was they wanted to build it local. They wanted to build it in Wellington. And in the end, they ended up building it about 5 kilometres from the wharf that this ferry will actually operate on. And so this is our vessel. And actually from the drawings that you look at here, nothing particularly remarkable in terms of what you see. But the only thing is that the helm station's on the port side, which is a east by west special. Other than that, to the ordinary commuter, it looks like an ordinary vessel. You've got nice orderly rows of seats. You've got somewhere to get a cup of coffee at the front. But other than that, she looks like a standard vessel. She is 20 knots, So that's roughly 40 kilometres an hour, which is slightly faster than the average commuter vehicle on the traffic out there. And obviously it has the advantage of being able to go straight across the harbour. It's 19 metres overall and 135 passengers, although some of those guys are on the uncovered upper deck. So most of the commuters are down on that lower deck. But it's beneath the skin where this vessel starts to get a little bit more interesting. And it's the first of its kind in the Southern Hemisphere, both due to the speed and the size of where she is. And she's a radical departure from what's actually available out there on the market at the moment. When she goes into commercial operation later this year, she will be New Zealand's first high-speed electric ferry in service. And I mean all electric. We've got no internal combustion engines on board at all. This is not a hybrid. There's no backup. Everything is driven off the 550 kilowatt hours of installed lithium batteries and a series of backup batteries for redundancies. And to achieve that, the lower hulls, everything below that passenger deck where the passengers experience, is literally crammed full with high voltage DC power equipment. She runs a 750 volt DC distribution bus to drive the two motors and has the capacity to accept over 1400 amps from a 1 megawatt charger when she's alongside the wharf. That high charge rate is what allows her to do a normal commuter run with a less than 20 minute turnaround after an hour cruise while they load and offload passengers. The energy storage system is liquid cooled, and the primary reason for that is to allow you to accept that high charge rate safely and securely over a repeated amount of time. The battery pack itself, or the energy storage system, which you can see here in the forward hulls, is around 6,000 kilos total on the boat and is one of the largest installations of its type here in New Zealand. And those batteries sit within a 30-minute fire boundary, and the Mackays who did the design and integration of the electrical system took a safety-first approach from the beginning with the electrical design, providing multiple layers of monitoring, of protection, and built within the composite structure itself is a unique fire boundary and access hatches for getting these batteries in and out if you need to access them. And the second thing, obviously, is that this boat is built entirely out of carbon fibre. This materials combination is obviously pretty familiar to a lot of people, and particularly in areas such as the America's Cup or Formula One car racing, but it's still an anomaly in commercial vessel surfaces. With the aluminium industry, the main contributor to commercial ferries. So you can see pretty clearly in these photos that instead of the normal silver, we've got black everywhere you look, from the stem right to the carbon fibre rudder at the back of the boat. And I guess just quickly for people who aren't familiar with composite construction, I mean, we've got some samples down at the back, but you've got three basic fundamental components. So you have your fibre. Now your fibre is what provides the strength to your material, and it comes as a dry fabric. Now e-glass is the mainstay of the marine composite industry, relatively low modulus, medium strength, and low cost. A carbon fibre, and that's what we're dealing with here, is a high performance fibre. It's extremely strong, extremely stiff, and fairly lightweight as well. There's another other specialty fibres, but those first two are the main two that you're going to find. Now, the second component is obviously a thermoset resin. Now, in this case, the boat was built for infusion, which is where the resin is forced through those fabrics using vacuum consolidation. The resin cures solid, and it binds the layers together and turns the drapable fabric into a rigid structure. For this boat, we went for epoxy resin for strength, for its high strength and toughness. The other common resins that you might see in the marine industry here in New Zealand are also vinyl ester and polyester. And probably the last piece of sandwich structure is the structural core material. That's a product that ranges in density anything from 60 to 130 kilos, and this is really the key for what enables you to build lightweight marine structures. The core provides the separation between your two layers of carbon skin without any significant weight. For example, most of the structure above the waterline of this boat is made of an 80 kilo foam core. Everything below the hull ranges between 100 and 130. I think we're a room full of engineers, but just in terms of principally how that structure works, the sandwich structure is the same as an I-beam, but applied to a structural shell. The high stiffness and strength of the carbon fibre skins is what takes the tension and compression. The low density core in the centre is there to provide the separation between the skins, to stabilise those skins and to carry the shear load. And so that's the technology that enables you to build a large self-supporting lightweight structure. And for example, the structural hull of the vessel that we're looking at today is in the order of 8 kilos a square metre. And so lightweight is the primary advantage that we're looking at for doing a carbon fibre structure. If we look at this graph here, it gives you a typical weight study, actually here based on aluminium as the default material in industry. On the left-hand side, you have steel. Now, steel is obviously a cheap material. Fundamentally, it's heavier. And that's why you see it in larger, slower ships. You don't often see it in a high-speed vessel. Now, if we move to the right, that's where we go into composite construction. First one is what we're talking about, the sort of 1970s composite construction, all e-glass and resin, no foam core. Actually pretty much equivalent to an aluminium weight. But if you move further to the right, you add that foam core into the middle of the panel, and you can start seeing the reduction in weight you can get down below 80% of the aluminium structure if you're an e-glass foam, and down to 60 or even 50% if you go to a carbon foam structure. Now, there are other reasons that you might go composite, particularly in the marine environment. It's a corrosion-free material. It's also fatigue-resistant. When it's in a dry fabric, it's formable into complex geometry, good thermal geometry, but lightweight is the real key that you see used in structures. And actually, for many years, I've been using this graph as a way of explaining the uptake of advanced composites into transportation projects. And in particular, the early adoption of composites as parts, moving through to full composite structures in both aerospace and the car market, basically tracking along with fuel prices. By comparison, the marine industry was building full composite parts back here, but it never really translated into commercial vessels. And interestingly now, though, that conversation has shifted away from the raw fuel cost more to this sort of graph. Oil's no longer at the $100 a barrel that we're looking at on the last screen, and the focus has shifted much more firmly onto what we can do to reduce CO2 emissions, which, as you can see here, have grown year on year in line with our population. And it feels like now more than ever, there's a lot more momentum around taking some positive steps to actually becoming a carbon neutral, or even approaching carbon neutral by 2050. And from the trends, you can see there's some work to do. First, to stop the emissions from rising, but from some numbers that you see, people are asking to reduce CO2 by 6% year on year for 10 years to get these numbers to half of where they are at the moment, which is one level that they think might be sustainable. And so this sends an increasingly motivated public, myself included, to go look at, well, what steps could they take to reduce their CO2 emissions. And if we look here, these are the New Zealand stat numbers from last year, which show the percentage of emissions from a typical household as a place to start. So keeping the kids home from school isn't going to do much to reducing the CO2. There's not really any point giving it wine or beer. It's not going to do much. But the thing that stands out is that transportation makes up the major part of any household's contribution to the CO2. And the numbers shown here is the sum of your direct and indirect emissions from transport. So the direct being exactly what comes out of your exhaust pipe, and the indirect being the fact that that's an energy source that we've got from the other side of the world and encompasses all the energy that it takes to mine it, to refine it, to ship it and get it to the country. And indeed, on the government's own numbers, fossil fuel is still New Zealand's largest energy source. We imported around 300 petajoules of fossil fuels into the country in terms of energy. 200 of that went into the domestic transport fleet. And so for the average Joe wanting to look at ways of reducing their carbon footprint, this is the pretty easy target to go. Now you can do that by upmoding. You can do that by going from your car to your bike, from your bike to walking, or moving to public transport. The automotive industry is already heavily investing into high efficiency electric vehicles, even if we then go and buy SUVs instead. But the marine industry and commercial vessels have been much slower to adapt these technologies. So in seeking to improve that performance of that marine vessel, it's important to understand what goes into those numbers. And the first thing is utilization, so the utilization of the vessel. And what I mean by that is the number of passengers on board at any given time. Now, for your average commuter ferry, it's going to go one way completely full, it's going to go the other way completely empty. So as a result, its utilization is very low. You're burning up all those kilowatts without any passenger miles being attributed to it. And the second that comes into play there, once you look at that utilization, the key is making that return voyage as efficient as possible. And that means reducing the dead weight of the structure, taking out anything that's not specifically necessary for getting those passengers across. Now, vessel efficiency itself has a role to play, and here I'm talking about driveline efficiencies, talking about hydrodynamic efficiencies, and so forth, and energy conversion. And finally, there's also managing acceleration and deceleration. Now, a ferry doesn't do much of either, and so for marine structure, that comes down to minimizing movement of. And there's one thing when you're talking about a composite boat, a lot of people automatically start thinking about luxury yachts, about race yachts, and I guess that's not what we're talking about here. A lot of those structures rely heavily on female moulding, on large moulds to get that curvature and that shape, and that's not what we're talking about here. We're talking about building a composite boat in a very similar way that you'd build an aluminium boat. So relying majority on flat panels, minimizing the amount of tooling and molds to where it's absolutely critical in the hydrodynamically important areas, and then producing a boat that looks similar and has the similar versatility of an aluminium boat. You're not tied into the same geometry over again. And so at a preliminary stage, we actually looked at 3 identical structures for this vessel. These little cutouts here are the pieces that are on the back, just to the right of the wine glasses on the table there. We designed the structure in a typical aluminium frame and stringer construction. We did an E-glass foam core and a carbon foam core structure. And the importance of doing this design was to look at the relative weight savings that we could get out of the structure. And so for the basic design concepts, we calculated a structural weight, which you can see down the bottom here. So in terms of a full vessel structural weight, aluminium, we're at 100% structure, which is across here in the blue, down to about 75% of E-glass. And then we looked at carbon and the carbon electric options, where we're down to about 50%. Now you notice in here, the first 3 models are all conventional diesel drives. There's slight differences in the insulation requirements just between each material as you juggle between fire insulation and thermal insulation. Now, in terms of fit out, you'll notice all 3 of these are the same. They're all the same diesel motors. Over on this side, you can see the significant increase, which is predominantly caused by the energy storage system. So you've got around 6,000 kilos of batteries on board. Slight difference in payload. Payload being the variable loads. All the diesel ones have fuel. It doesn't matter how much voltage you put onto electron, it doesn't get any heavier, so there's no variability of fuel load on the electric ferry. Obviously, what becomes fairly clear on this project is on a vessel that's operating for 20 years. Now, a lot of people might look at 20 years and go, that seems like quite a long time, but the vessels they're already operating have been in there for 15 and 20 years respectively already. And what you can see is how dominant the energy or the operational costs, and a big portion of that is directly down to the fuel source. As we move down the technology levels, that displacement reduces, so does the energy. Now, the big difference between all the diesel ones and the electric one is twofold. So for every kilowatt hour in electricity, at the moment, it's between 1/2 and 1/3 of the same kilowatt hour that you're going to buy in diesel. So there's a reduction in raw energy cost. Within the diesel engine ones, there's obviously quarter life, half-life, regular servicing and engine replacements at 50,000 hours. In the electric one, we've got the issue that at 10 years, we're going to replace the whole battery set with a new set. But nevertheless, the operations costs far outweigh any of the other structures. Now we're still asking, and I guess the one other person to look like is we went to carbon diesel in terms of emissions. Over the life, there's going to be around 9,000 fewer tonnes of CO2 emitted, purely by saving weight, still staying with diesel. the option of going to carbon electric. That's down to 25,000 tonnes of saving. And so the conclusion of that study was initially that actually either e-glass or carbon structures returned a significant cost of operation over the life of the vessel. When we looked at the structure using a net present value analysis, looking at the fact that we're still asking the end customer to spend more upfront with the promises of future saving, actually the carbon diesel on a pure numbers essence came out slightly ahead. So it had a payback period of around 3 years when it started returning a positive net present value. The carbon electric vessel, because of that higher capital cost, took nearly double that, around 7 years. And so that requires an operator to have a certain level of confidence that they're going to continue to operating that vessel over the long term. If an operator has a short availability or a short contract on their term, fundamentally they're always going to go for the lowest capital cost vessel. But on top of that, so luckily East by West did have the long tenure that they were going to survive, and also they showed a lot of interest in this reduction in CO2. And obviously as we move through that technology level, there's that massive jump. So the 14,000 tonnes in direct emissions, that's in the Wellington environment, and 25,000 tonnes overall. And so we're fortunate enough that they kicked off the design as a carbon electric boat. And of course, now that we'd got through all that, the next phase was actually getting into the construction. And in particular, how the builder wanted to build this vessel in Wellington. Now, at the time we started design, there was no builder in Wellington big enough to actually build this vessel. So they did what a lot of good New Zealand boat builders do. You start with an empty shed and you get on with it. So at the time that we were starting to design, Webb set up their facility and they started hiring people. Now, as you can see, for the age of the other boats in terms of how quickly this customer is replacing the boats, this isn't something where they need 10 boats a decade. So the builder needs to maintain a structure that's nimble enough that can address those customers and meet the demand when it's needed. And to address that, a modular construction technique was used for the boat, which relied heavily on digital manufacture to make that work. This was used to reduce the required composite resource at the boat builder's end and to make it fast and reliable construction. For this first boat, this actually involved Gurit in a product called High Panel, which is where we essentially pre-make a kit set of CNC cut flat panels and supply that directly to the builder for assembly. And the process starts right from the design stage in terms of identifying what is suitable to kit set and what isn't. What's going to be supplied as a CNC kit, what's going to be built locally, and then splitting up the geometry on that basis. And the key with digital manufacture is that all of the aspects come from a single 3D model, from the geometry to the system, to the tooling, to the jigs that you're going to assemble the boat on, relying on a single shared point of geometry to ensure accuracy. The top two drawings here show the MDF jig going together in the design stage within the 3D model. These panels here are the high panels, so these are the pre-made CNC panels that are going to get made. That gets modeled up in 3D, and at the same time you've got designers nesting panels for either manufacture here at the builder or manufacture at the high panel plant, and nesting those panels in to reduce the wastage during manufacture. And that single source 3D helps to ensure that the geometry is accurately enough that you've got easy assembly later. And so then, parallel to those panels being made in one factory, you've got the boat builder setting up that CNC cut jig at their end. Now, unlike a conventional composite structure where you might have to build a full surface mold to make that part, the stability of the pre-made panels means that you can really minimize the amount of panels, the amount of structure that goes into that mold. That helps reduce ultimately the amount of materials committed to that mold. It also allows the builder flexibility in that this mold can not only be taken down and stored, but relatively easily modified. Somebody wants a different door or a different window position, so for future builds. The next phase with the tool built, now the panels start arriving, and because we're dealing with a lightweight structure, we're able to make really large panels. So in this case, the whole top deck is actually built in 4 panels, the largest of which is 9 meters by 2 meters, and that's still manhandleable. It takes a few people, takes a few hands, but you can maneuver it up onto the place. Now that big format means that you don't have as much parasitic weight from joining. Also means alignment and assembly goes pretty quickly. Second big advantage is those panels are stiff enough and rigid enough as they are there that it's walkable while it's sitting on the mould. So that gives you access to other parts of the mould. Now more panels get fitted. As you can see, the jig incorporates a lot of features for some moulded components and also for the structure to go in behind the panels, all fairly precisely cut and in place. Details you can see here, such as hard points, can actually go in when the panels are being built, or the builder can cut them in lately. And the precision and control of the geometry allows the builder a much greater level of flexibility in the design and the build of the vessel. In particular, in this case, it enabled the builder to start building the flybridge. The whole upper deck was started before the designers had finished the hull lines for the vessel. Obviously, depending on what the electrical engineers were going to put in the hull and how many miles of copper wire they needed to run out, which was quite a few. But this allowed the builder to start building while the designers continued on the hydrodynamic analysis of the hull. And then the final step is bringing in, of the modular construction process, is bringing in other sub-assemblies. So in this case, these were moulded seats. These were built, again, using a kit set they were moulded because of the repeat geometry. Those were built in a whole separate production line, brought in and fit once that top deck was completed. Now the hulls we mentioned before, the hulls weren't a candidate for building at a flat panel. This is the bit where the naval architects really wanted to drive up the efficiency of the boat, and so they wanted a curved hull. In this case, we used direct cut CNC hulls. So again, compared to a conventional method of building a plug, building a mould and taking it off, you reduce wastage in time by going to a direct cut tool. In this case, what you can see here is the hulls being infused. It's a split half mould on one side. So you had two moulds of which you produce 4 parts from. And again, this tool was cut well after that flybridge had already started. And then you paint it, stick it together, put it in the water. Obviously, there's a few more bits and pieces that go into it than that, but here you can see the boat in the water. This was on Friday, sitting nice and level, which is what everything want to see, and she's going to be ready for operation probably within the next month. So the second big draw card of using that method of digital manufacture in modular construction is that's now a construction method that the builder can deploy almost anywhere in the world. He's got the geometry, he's got the process drawings. It's obviously not a particularly convenient structure to ship any large distance, so that ability to capture that digital information and to transfer it allows this builder to then build that boat in market if they need to. And so there she is. That's her about to go in the water. She's currently undergoing the final checks with the programmers and the electrical engineers. And we hope to see her in commercial operation very shortly on the Wellington harbour, and offering our commuters a silent, vibration and exhaust-free experience across the harbour. Thank you.
Well, that was fantastic, Tony. So I think we've got a few minutes now for any questions from the audience. Do we have any questions? You're closest, sir.
The capital cost of this one compared to conventional aluminium, that was 80% extra. Is that what I read from your?
Yeah.
Okay. If it was done if it had conventional diesel drives?
Conventional diesel drives are about 30% extra.
Okay. Probably. And the labour component,
yes,
building compared to an alley boat?
It's higher. So that's included within this blue section here. So yeah, there is a higher portion of labour cost in the composite boat, even once you've taken the same approach as the aluminium boat with the flat panel construction. Ultimately, there's still additional finishing steps and filling and fairing. Now, the East by West Ferry, they really minimise that in terms of not getting tricked into the trap of trying to make it look like a super yacht. it's a commercial ferry, like an aluminium boat where you might have expressed welds. They're a bit better than an aluminium boat, but they've tried to find a happy balance there.
Thank you. Was it twin prop, I presume, out the back? And was there any special attention to the prop design and rudder design?
Yeah, so it's got, again, for a power boat, it's got quite an unusual rudder. So it's got a carbon fibre rudder stock, again, to save weight, but it's also got an aerofoil section rudder, again, to minimise appendage drag. Propellers are conventional propellers, just again for chasing efficiency. We did look at jets for the vessel, but you give away another 5–10% of propulsion efficiency. And with twin props and the separation that you've got between the props, the vessel's extremely manoeuvrable without the jets.
Thank you.
Thanks, Tony. So from a composite design construction, was anything particularly different about this to other vessels, similar vessels?
I guess two was making sure that we were designing stuff that was as buildable as possible. So because it's not a no expense spared super yacht, we had to make sure we kept to that. Actually, Gaspar here in the audience is the guy who did most of the engineering work. And the second one was actually coming up with a lightweight fire solution. The batteries themselves, being liquid cooled, are extremely safe batteries, but this is also the first vessel that Maritime NZ has certified with a large lithium battery bank on board. And so coming up with a lightweight solution to the composite boundary, but also to the composite hatches and the racking system. So we saved around 700 kilos by replacing the steel battery system, battery cage with a carbon composite battery rack. And we also use that rack to provide additional fire protection around each of the subpacks.
All right.
How many times can you get across the harbour without recharging your battery? And what sort of storm conditions can you withstand without going flat before you get home?
So it will never go flat without, knock on wood. So it's got a control system on board which continually monitors battery condition, and if it got to a point where it was having to, it monitors the amount of energy it's got left and how much it's got. One advantage of a displacement hull form like this is you've got the ability to tailor speed and power quite readily. On a normal run, it'll run there and back, so it'll run for an hour before it needs to recharge. And that's within the safe operating levels of the battery, so well below, if it was an emergency, we needed to go home situation. But yeah, it'll go there and back, so it'll run for a full hour at 20 knots.
How are the batteries for seawater inundation if the worst should happen?
So the batteries are completely sealed units, so they're able to
all independent. And
yeah.
Thank you for your presentation, Tony. Just had a question. Are you monitoring the energy consumption and doing a kind of verification of the savings versus diesel, etc., that kind of thing for future, for marketing or whatever?
Certainly, the